The final issue in section 2.4 is kind of an informal version of hypothesis testing. This came in chapter 2 of the book before we knew what hypothesis testing was. So it's a little surprising that they even brought it up that early in the book, but it fits in with today's material, and it's tested. So here we are. So as always, the issue in hypothesis testing is we might take a sample and look at that sample and find out that there appears to be a correlation between X and Y in that sample. Now, what would explain that? Did we just get a lucky sample? Or does it reflect a true correlation throughout the whole population? Well, we're going to test that by figuring out what R is. R is also associated with the p-value. And as usual, we can do our hypothesis testing in one of two ways, one-dimensionally or two-dimensionally. So we would find a critical value of R. Critical is indicated here with a little asterisk. And that could be found in a lookup table, for example. And then if the sample's value of R exceeds that critical value, this would give us sufficient or significant evidence that X and Y are correlated throughout the whole population. Or the two-dimensional version of this would be that we could find the p-value associated with R, and in this section that's going to be given in the problem. And then if that p-value is less than the significance, meaning a smaller tail area, that would give us significant evidence that X and Y are correlated throughout the population. So in this section, we don't have to do any calculations. These numbers will just be given to us. And let's take a look how that would look in the examples. All right, so back to our illustrations and examples sheet. A sample is often used to test the hypothesis that X and Y are correlated throughout the population. The smaller the sample, the higher R must be to convince us that the correlation we found is significant. As a silly hypothetical, for example, imagine that somebody only took a sample with 2 points in it. And they said, look, these 2 points, they're on a straight line. That proves a significant linear correlation. I think that you would probably realize that that argument is baloney, because you can draw a straight line through any 2 points, right? That wouldn't be very convincing. Or if they took a third point, any 3 points is always going to be a triangle. And it's always kind of easy to draw a line through the middle of a triangle and say, look, there's a straight line pattern here. So when the number of data points is very small, you would have to show me that they are really, really, really strongly correlated in order to convince me that they really represent a correlated population. The more data you take, as usual, the less you have to convince me, because it becomes increasingly unlikely that samples that large would be correlated if the population was not. So notice that the critical value doesn't have to be super high, and as the sample size increases, that critical value gets more and more relaxed. But anyway, we look at the sample size to determine how large the critical value is, and then basically we're going to compare the actual value of R from our sample to this critical value and see if it's large enough to prove significance. Okay, so example number 1, a website reviewed 10 different brands of disk drives. The specifications included in the review included the price and the memory capacity of each drive. So those are our two random variables here, price X and memory capacity Y. Stella, the stellar statistics student, was so bored that she calculated the linear correlation coefficient, R, between price and memory. She found that R equals 0.719. Question A, what are the critical values for Stella's sample? Critical values, again, mean before we even look at the sample, what's going to be our cutoff point for convincing us of a significant correlation? Okay, so that depends on the sample size. In this case, it says Stella used 10 reviews. Okay, n equals 10. And therefore, the critical correlation here would be 0.632. So that's the number I'm looking for here. It just comes right from the table. All right, now we actually look at her sample, and we find out what her sample says. According to her sample, she got a correlation of 0.719. Has Stella found sufficient evidence that the prices and memories of all brands of disk drives are significantly correlated? What equation or inequality justifies this? Well, the answer is yes, because the R that came from her sample was big enough to exceed this critical value. By the way, I forgot something. Let me come back to this now. Notice that this question is pluralized. What are the critical values for Stella's sample? So the answer to that would be plus or minus 0.632, because whether the correlation is positive or negative, it needs to have the same absolute value to be convincing. Okay, so remember that the inequality that we're actually looking at here is the absolute value of the R we get from our sample has to exceed the critical value. And in this case, it does. And therefore, yes, we have sufficient evidence that prices and memories are correlated throughout the population of all disk drives. So that's a one-dimensional hypothesis test because R is just one number on a number line. Example number 2, we're going to take this two-dimensional and look at tail areas. Several hundred lab rats are measured for the amount of caffeine in their system and the amount of time it takes them to run through a maze. Okay, X caffeine, Y time. The p-value for these measurements is 0.008. And again, remember in this section, we don't need to calculate p-value. It will just be given to us in the problem. Okay, A, this p-value indicates that if caffeine and time are not correlated, then the probability of selecting a sample with a correlation at least this extreme is what percent? Well, that's exactly what p-value means, doesn't it? So, as a decimal, p was 0.008, or if we turn that into a percent, that is 0.8%. I sometimes like to fill it in this way. 0.8 of a percent, less than 1%. B, how does this probability compare to a standard significance level? Well, we usually use significance levels, alpha, that are between 1 and 10%. So whichever significance we use, this one is clearly less than that. C, therefore, is there sufficient evidence that caffeine and time for all rats are in fact significantly correlated? So again, here the answer is yes. And this time it's because our p-value is small enough. The relevant inequality here is if p is less than alpha, we have significant or sufficient evidence of a correlation. So the upshot here, remember the takeaway. Significance is demonstrated with either high test statistics, in this case the test statistic is R, or low p-values. A high test statistic is one way of saying that you're far from the middle, or a low p-value means that since you're far from the middle, you're cutting off a very small tail area.